Good evening, ladies and gentlemen. Welcome to this very interesting event, a presentation by an expert in the field on benefits of vanadium redox flow battery for utility scale batteries in South Africa. This is a joint effort by the Load Research Chapter and the Battery Storage the energy storage chapter of SAIEE. The two chapters, the load research and energy storage, are mutually connected chapters which are working towards the betterment of energy sector in South Africa. We are working towards many development and promotional projects. And today, this event will be chaired by me. I'm Chandima, a professor from Wits University. And I'm also engaged with several other institutions, and also the present chair of the energy storage chapter. And before introducing the eminent speaker today, let me tell you a few words about the motivation of this lecture, which is one of the series of presentations that the two chapters have been conducting separately, individually, for the last 1 year, I may say. We have been promoting this field, the respective fields, for the hard period that we have passed in the last year and a half, and we are trying to make the field of load flow, the energy storage, which are mutually interconnected fields of electrical engineering, to be successfully implemented as a main solution for the power and energy issues that we have in the country at present, so that the load management is very much augmented and supported by the energy storage systems. And what we envisage is that South Africa needs its own indigenous, I may use the word indigenous because we need to develop our own systems, not purely indigenous, but knowledge channeled from the international level, blended with the indigenous knowledge to implement or to come up with viable solutions for the energy and power issues in the country. And the two chapters are working their level best towards promoting collaborative research, adaptation of the most suitable and fitting technologies for the country, developing a platform to bridge the gap between the industrial sector, commercial sector, research sector, and the government, so that we are on a rather tough task, tough journey. And I would like to invite all of you, all attendees, and all interested parties and individuals to join our chapters and be a part of this very important and concurrently needed mission of providing South Africa a reliable and better power and energy environment. Thank you very much for your support. And now I would like to introduce our eminent speaker today. Mr. Frank Spencer is the head of deployment of Bushveld Energy. Frank is a well-known renewable energy personality in the South African renewable energy space. He currently is the head of deployment at Bushveld Energy, a vertically integrated vanadium redox flow battery company. So please note that this is one of the local companies which manufacture vanadium redox flow battery locally. This is the most important aspect of this company. I'm sure that Frank will elaborate it. He has masters in engineering in electrical stream, as well as a philosophy degree in sustainable development. So interestingly, Frank is both an engineer and also a sustainable development degree holder. This interesting combination of academic knowledge, I'm sure that has made Frank one of the most interesting and effective speakers in the country. Frank, over to you, and I would like to change the presenter mode to Frank. Can you please help me?
Thank you, Professor, for your kind words. When I was studying, I was accused of being an engineer who could write. So I'm not quite sure what that meant, but it did mean I went on to do a lot of writing when undertaking those philosophy studies. And it's a pleasure to be here. So thank you to the SAIEE and the team there for having me tonight. I believe we will be able to take some questions at the end, and I've got quite a lot of slides to get through in the time. So I'm going to move quite quickly. I'm sure this presentation will be made available afterwards, but if there are any questions, maybe just note which slide it is, and I will then go back to that and perhaps answer the question. Really what I want to walk through in the agenda is just having a look at what's happening with energy storage globally, where vanadium redox flow batteries fit into the picture, how the technology is developing around price and performance, and what's happening in the South African space, both for energy storage and for vanadium redox flow batteries. As was mentioned, yeah, I'm an engineer, although I built my first solar project at school many years ago, but did my first rooftop solar PV project already 21 years ago, and a big off-grid project in 2003. So was messing around with solar and inverters long before it became fashionable or cheap. Solar modules have come down something like 10 times or 50 times in Rand terms in the last 20 years, which is quite phenomenal. And it's really been amazing to see in the last few years how both globally and in South Africa, renewables adoption is growing. And growing rapidly, and absolutely we know that this is a need, that all the science around climate change and carbon emissions is pointing to the fact that we need to rapidly get off fossil fuels and get onto clean tech. And you can see on the graph there on the right that let me just get the pointer, that even with our best commitments to date, we're still massively missing the reduction target that is necessary. So there is going to need to be significant investment in technology change as we transition away from fossil fuels to a new paradigm. And that may be happening already. We're seeing that electricity is becoming a more and more important component of the energy mix over time. We're hoping that this will accelerate even more. It does need to meet that pathway I showed on the previous slide, and expecting that renewables will play a bigger and bigger role in providing that energy. Again, we actually need to be more aggressive than this to meet the 1.5 degree target that is required by science or the emissions below that, to keep temperature below that. And electricity is primarily being used in 4 different roles, and a lot of it is related to stationary devices. You can see the grid connected, commercial, industrial, mining, residential. That's really where most electricity is going to, although electric vehicles are likely to become a huge portion of that in the near future as well. And in the energy sector, perhaps the fastest growing technology at the moment is around storage. You can see the sort of in terms of where storage is going to, it's likely to remain mostly in transportation, but we can see that the stationary storage section is growing tremendously at the moment, and that's all the grid-tied batteries that are being deployed. And that trend is likely to continue. Certainly, even in the last couple of years, we've seen that the size of storage has grown quite significantly, even in 1 year, and that's perhaps the most common technology, lithium deployments, basically doubled in 1 year, with other technologies being deployed as well. And this rate of storage deployment is only going to go faster and faster. And it's because of all of the values that energy storage can create. And certainly, as we know, with renewables, we need to smooth out the generation for the times when the sun isn't shining or the wind isn't blowing. And in South Africa, a lot of modeling has been done around that. And what we're seeing is that we can achieve a least cost pathway that is predominantly renewables, with lots of solar, lots of wind, and some storage to get us there. So let's talk about where batteries are being used. In this slide, we're basically seeing, in a sense, energy on the one axis at the bottom, and power on the vertical axis, and seeing the different sort of applications that in short-term storage is being used for sort of grid services, and really at the long end, you're getting long-term storage, energy storage, and perhaps the off-grid systems sitting in the hour to day sort of space. And if we carve it up into where those technologies are playing, we're perhaps the one we're most used to is the pumped hydro, but we're starting to see that battery storage or electrical type of storage starting to merge very much right from the small systems up to the 100 megawatt type systems, typically in short response times right up to day-long sort of batteries. And in this space, we're seeing lead acid still playing a big role, a whole bunch of other technologies emerging, lithium ion playing a large role, but really expecting flow batteries, in particular vanadium redox flow batteries, to be playing in this long duration space where batteries are running for 3-4 hours plus. And certainly, for example, in South Africa, in the commercial and industrial mining space, one of the applications is for tariff arbitrage, and right now that's a 5-hour business case, which well suits flow batteries and vanadium batteries. Of course, the batteries can do a whole lot of other services as well, and I've mapped out, or at least on the slide, there's a lot of what those services are that can be provided to the grid. So it's not just about energy, it's also about frequency regulation. And I'll talk a little bit about inertia in a second. I think inertia has been a controversial one with inverter-based technologies, but even there, inertia on the grid is starting to be provided by the inverters working with batteries. Certainly in South Africa, we're seeing in the private sector, the use case that I just described, which was for tariff arbitrage or time shifting, but also to massively increase the level of renewables penetration in private projects. And you know, because you can now charge the battery with excess solar during the day, you can redeploy that power into other times of the day. And those sorts of projects are already starting in some cases, and certainly in our own project that I'll talk about a bit later. And of course, we're well aware that the utility Eskom has also well recognized that storage is going to play a big role across the distribution network, across the grid. They've run their first round of procurement. We're hoping those results will be announced soon. And it's certainly very exciting to see that sort of procurement happening in South Africa as well. I put in a particular slide around inertia, since that's been a big item of discussion recently about whether or not inverter-based technologies can provide the right level of inertia compared to synchronous generators. And we're certainly starting to see that the newer generation of grid-forming inverters can do this and can do it very, very fast. And what's also exciting about it is that for the same amount of capacity they can provide significantly more inertial response. You can see that sort of the orange comparing a same-sized inverter-based system to, say, a gas system. And the conclusion there from this report by Fluence was that yeah, it's almost 10 times as much inertial response that can be done by power electronics, by inverters, rather than by synchronous gas. And again, the capacity that same power plant can provide, if you've got, say, a gas generator, you have to run it between a minimum and rated capacity. And obviously it's just generating, where with storage, you're getting almost 4 times the amount of grid effect that the battery can do because of its ability to both charge and discharge at full power. And that can be used to do ramp rate smoothing, you know, being able to provide basically double its capacity to the grid on demand versus, say, a gas generator, which has to run it between a minimum capacity and its rated value. In terms of technologies that are actually viable today for South Africa, I think the two that stand out are obviously lithium ion that we are seeing deployed and will continue to see deployed, and that flow batteries, and particularly vanadium redox flow batteries, are also starting to emerge. There are numerous companies now around the globe providing vanadium battery solutions, whereas a lot of the other technologies emerging are still in early stage commercialization. So it's very exciting that in South Africa we can do a lot with vanadium, and I'm going to talk to that in a sec. So yeah, let's talk about the actual VRFB and how it works. Basically, you can see a description of or picture of the battery there, where there's a stack in the middle. There's a membrane in the middle of the stack, keeping the two halves of electrolyte apart. You have one electrolyte shifting between +3 and +2 as it absorbs an electron, and the other electrolyte as it gives off an electron, going from +4 to +5. And that electron obviously flows in the circuit, and you get a hydrogen atom moving across the membrane as well. But I think this video perhaps will explain it way better than me if it plays. Let's see if it works. So I hope you caught there, perhaps one of the most important things about VRFBs is that there's no degradation in the electrolyte over time. So that's super exciting for batteries that want to run hard on the grid for a long term. But I'll talk a little bit to that again in a little bit of detail in a moment. I think the one fact that got left out in that short little visual is the exchange. There is a hydrogen a molecule exchange over the membrane to keep the electrical balance in play. In terms of where projects are happening, China at the moment is by far the largest adopter of projects over the last sort of 4 or 5 years, with some very, very big projects being deployed. You'll see a couple there of sort of in the 10 megawatts, 40 megawatt hour class, but there already has been, and connected to the grid, already a 100 megawatt, 400 megawatt VRFB, and there's another one under construction at the moment. And I'll show you some pictures of those in a moment. And we're also seeing quite significant batteries being deployed elsewhere with other, leading edge IPPs and technology developers. So this, VRFB is really talking about going to the big scale in terms of batteries. In fact, this 60 megawatt hour battery in Japan, built by Sumitomo, has been running already since 2015. Which was quite a bit before Elon Musk's famous Australian battery. And yet this battery is still running exceptionally well 7 years later, proving the fact that at this sort of scale, electrolyte doesn't have degradation. You can see in this particular case, the electrolyte is kept in pretty massive tanks in a custom-built building for the battery. I mentioned those 2 Chinese projects. Yeah, the 2 of the biggest projects in the world in terms of megawatt hours. One already operation and the other one under construction again. And again, you can see actually here they have the power units containerized within the building. Those are actually sitting typically on the 2nd story, where on the ground floor you would have the tanks with the electrolyte. And to talk a little bit more to what really gives VRFBs, I guess the unique selling points is as I mentioned, is the fact that there's no degradation on the electrolyte. So you can buy a VRFB, you can have it run for 20, 25 years in a project, and the electrolyte will basically be as valuable at end of life as the beginning, and having not lost any of its capacity. Excuse me. You can also run it from 0 to 100% full use. You can do that multiple times a day. It also doesn't affect the life of the battery. There's no risk of fire. In fact, it's more likely to put a fire out since the electrolyte is mostly water. It's a sulfuric acid with the vanadium captured in it, but there's nothing to burn. So that's a big thing at the moment where, lithium technologies, there's been a lot of risk with fires, and that's leading to insurance companies putting up the cover quite significantly, the cost of cover on lithium batteries, something that VRFBs don't have to worry about. And I mentioned that electrolyte, that after its use, after 20 years or however long the project is, it could be redeployed into a 2nd life battery or a 3rd life battery or 4th life battery. That electrolyte can remain usable from a circular perspective, or it can be relatively easily reprocessed to extract the vanadium. And unlike other flow batteries, where if you had your 2 sides, your 2 tanks mix, it could cause significant problems for the battery, because the electrolyte in both tanks is basically the same. Even if you do get some cross-contamination between tanks, there's no problem with that. And I've already mentioned like the very big batteries, and also that the DC side of the batteries can have and do have a very fast response time. And if it's typically the inverters that can then be designed to provide even faster response times of the energy stored in their own DC bus. I'm not going to go into all of the details here. You can have a look at this, but comparing VRFBs to lithium, but really VRFBs are well suited for long duration applications. They do have the value that the power and energy is decoupled, because the stack set up the power or the megawatt rating of the battery, where the quantity of electrolyte sets up the megawatt hours or the duration of the battery. And I think the long duration nature and the lack of degradation really, if you do an LCOE comparison versus lithium that's regularly augmented, can give very good results. Yeah, I won't go too much into the performance benefits. This is just some slides showing the degradation of lithium versus the measured degradation of vanadium. You can see actually when they measure it, it's going up and down. It's actually not degrading. That's got more to do with temperature effects at the time of measuring the energy. But yeah, basically in the long term, this is from that Sumitomo battery in Japan. The electrolyte's not degrading. So really, yeah, where we see VRFBs playing is in that long duration space. Looking at this graph again, basically from the 4-hour to say 16-hour range of storage requirement, right up to the 100 megawatt level and beyond. That's VRFB's sweet spot in terms of performance. Yeah, so just to talk to the vanadium as well, or the growth of batteries, we can see that one of the challenges is the demand for minerals. And in fact, that's a constraint on lithium batteries at the moment that is driving up the prices, that there isn't a volume required. Basically, you can see in this, there's two different analyses showing what the 2030 and 2040 volumes for batteries could be compared to today. And you can see it's just, the volume of minerals required is already like 2 orders of magnitude more of what it is today, and the growth rates are going to be, to meet that demand off the charts, and we're seeing that it does take some time for the mining sector to ramp up to meet that. You can see on this slide there's a whole bunch of minerals that are typically needed for the batteries. But what is really exciting about the vanadium is that there really isn't any lack of vanadium available. It can be mined quite quickly. So the reality is that VRFBs can scale very, very fast in terms of volume to meet the demand for batteries. That's just, again, playing to the safety side, that VRFBs have far better safety values. And I mentioned that, here's just an example of a number of fires that I've had with lithium that, as I say, have actually given insurance companies quite a fright, because lithium fires are happening more often than one would like, and other battery technologies as well. And then this slide is just to talk to the circularity again. I mentioned that basically once the vanadium is mined, it can remain in a circular process, either as electrolyte being reused in future batteries, or the vanadium can be extracted and reused for other processes quite easily as well. And this gives VRFBs a unique advantage, again, from a carbon footprint perspective, that their carbon footprint is significantly better than lithium typically. Plus, there's that real easy way to handle the end of life of the batteries with the electrolyte to redeploy the electrolyte. In terms of where we see, pricing going, we expect this is a little bit aggressive of comparing lithium with VRFBs, but because of that decoupling of power versus energy that I mentioned, the fact that if you want to add energy to the battery, you're just adding more electrolyte. As the runtime of the battery gets bigger compared to the hour rating, to the power rating, the price can come down quite dramatically. And again, it's not just about the price per megawatt hour. One has to look at the whole, how the battery is going to be used in a project. What is its use cases? How do those use cases stack up? What is the value of having a battery that requires no augmentation for 20 or 25 years? So actually, we've done a lot of work around this with clients to show them how, even though the upfront cost of a VRFB might be more per megawatt hour, with all the stacked value, and the fact that the electrolyte still has value at the end of life, that can lead to a significantly lower levelized cost of electricity. And I won't delve much into the levelized cost of electricity, except to say that it's a much better metric when comparing projects, comparing battery projects, rather than looking at the cost per megawatt hour. So this is the sort of modeling work we do for for any form of battery or battery renewables project. And I'll just put up some, some slides showing that renewables have basically got way cheaper than conventional power plants. So much so that and they continue to decline, that renewables have become dirt cheap. And the value of that, we're seeing the same thing happening on the battery side, basically, that battery prices are plummeting. And of course, the cheaper the energy gets, the less of an issue the losses in the battery become as well, in terms of round trip efficiency, because of course all batteries are lossy, losing energy, with energy getting so really cheap when available from renewables, that allows us to redeploy that relatively cost effectively with storage. And so we're seeing that VRFBs in some cases might be more expensive than lithium, but this is already 2-3 years old. We're seeing that this VRFB price is coming down, and this is in a short-term business case. When you start pushing it to 4 hours or 8 hours, VRFBs very quickly become cheaper on an LCOE basis compared to lithium. How are we doing on time? Let me just check here. 6:30. So we're also seeing that the demand from the utility markets is going to be, like I showed before, that sort of ramping and smoothing of energy, being able to support more generation. Those use cases are going to become quite demanding in terms of energy storage in the market, and the sort of quantities of storage that are going to be needed globally. Again, this is just showing how the sort of services that the grid is looking to use, and that all of these can be provided by batteries. And I spoke about that stacking of use cases. So this is something else we do a lot of work at, is look at what the value contribution is to a project if the battery is providing one or more of the various services that batteries and inverters can provide to a project. So let's talk about South Africa. We probably all know that most of the load is up in the northeast, with only less than a quarter down in the majority of the country in the southwest, and certainly that's where most of the generation is as well, or historically has been. And you can see the conglomeration of transformers up in the northeast and a few in the Cape. But what we've seen with renewables is that all the renewables want to be built down here, sort of in the north and the south of the country. And all the projects to date have led to the fact that the grid is now sitting extremely constrained. There is hardly capacity to build more projects in the area with the best renewables. So I know a lot of the renewables projects are looking to now move here, but the best resources remain here. And this is certainly something that, because the capacity factors of wind and solar are in the 20s, typically maybe in the 30s, if one deploys storage with those plants, you suddenly can create significantly more capacity for similar generation, and thus almost smooth out in a sense the capacity factors of those plants. So I think that's something we're quite excited about. We know that will have to come. That's almost transmission deferral by being able to move the energy to different time windows from renewables. And it's a bit ironic because a lot of studies don't show the possible growth in renewable, or at least in storage, that could be happening in South Africa. It hardly shows up on any of the maps, except when we look at residential storage to date. That South Africa back in 2020 was already the 6th largest market for residential storage. And I think that's, when I see how many solar PV and battery systems are being deployed into the residential sector as sort of load shedding mitigation and to sort of almost become semi off the grid, it's already a huge industry in South Africa. What we need to also be doing is bringing this up to the commercial, industrial, and utility scales as well. And certainly we're seeing that happen, that there has been the Eskom procurement program, hopefully to be announced soon. The RMI4P projects had significant amounts of storage in, and in fact, it's those PV wind battery projects that are most likely to close rather than the gas projects. And we're expecting more to come from the IPP office. So that already means like during this year and last year, we have a market around 1.3 gigawatts, which again, if you compare to this sort of slide, is actually huge and very exciting. And exactly, so 2022, things have been delayed a bit by COVID, but certainly South Africa could be on the map for utility scale deployments as soon as the Eskom projects get awarded and the RMIPP happens, and any future battery procurement that comes out of the IPP office. So yeah, really just a summary slide saying that there really is the opportunity for South Africa to become a massive energy storage market in the next couple of years as we phase out coal and gas and move towards renewables. And this is at all scales. We see how big the residential market is already and how big the utility market could become. In terms of localization, I had a smaller version of the slide before, but really showing that the growth expected for vanadium, while all of the battery minerals is basically off the charts, and the supply of this in this time frame to be able to by 2050 have this sort of growth in demand is really going to be quite a challenge, except for perhaps the vanadium space, and I'll talk to why in a second. Well, it's because we have a lot of it in South Africa. This is showing really the sort of reserves, but vanadium we do have almost, I dare say, almost an infinite supply. And what's really exciting is it is actually mostly vanadium that goes into a vanadium battery. Certainly in terms of volume, almost the whole battery is vanadium electrolyte, but you're talking about around 30% of the battery actually being vanadium in terms of its supply requirement. And then that does make it the battery with the highest single mineral demand requirement in terms of energy. But we have that in South Africa, and that's been, for example, it's been recognized in the SAIEE, the South Africa Renewable Energy Master Plan, that's still in draft, but really that why is this not working? There we go. That the whole value chain from vanadium, right from upstream to the full batteries, so making of the mining and first processing of vanadium, making the electrolyte, building the batteries, deploying the batteries to the projects, and then actually reusing the batteries again is the only battery technology that we can currently do from beginning to end in the South African space. And the reason why I say that we have almost unlimited vanadium is just the vanadium resources held by Bushveld Minerals is enough to build quite a lot of battery storage. So there's certainly no lack of vanadium in South Africa. It would really be a function of scaling up the mining. And since most of this mining is surface-based mining, it's relatively easy to do that. So certainly in the short to medium term, there shouldn't be any problems supplying sufficient vanadium to the demands of the market. So maybe just talking a little bit about what we're doing. We obviously have the mining side of the business, Bushveld Minerals, but on the energy side, the things that we're doing is we're building an electrolyte factory at the moment to make 200 megawatts per year. And I'll show you some pictures of that in a moment. And that already allows us to get to pretty heavy local content numbers for projects in South Africa, which is what we want. But also to export. This electrolyte factory called Belco will actually be the first dedicated electrolyte factory in the world. So that's super exciting that's happening in the East London IDZ. Then we've also set up a fund for the electrolyte, and that's because, as I said, as such a valuable component of the battery, it actually still has all of its value at the end of life of the project. But we know that project owners and battery owners typically don't value their assets that way. Typically, at the end of life, they would value the electrolyte probably close to zero. So this is basically like a commodity fund where we basically rent the electrolyte to a project, and we can do that far cheaper than a project could fund the electrolyte themselves. And so that really significantly helps projects improve their financials or their levelized cost of electricity. Then perhaps to correct the prof at the beginning, we're not actually looking to manufacture the batteries as Bushveld Energy, but we are looking to support as many of the manufacturers as we can. We want to see not only one company be successful, but the whole VRFB supply chain be successful. And this is why I've mentioned we're building the electrolyte to provide electrolyte to batteries locally. But we've also been doing a lot of work on supply chain issues, so that if a battery manufacturer does want to manufacture in South Africa, most of the supply chain is already in place for them to source all that they need to put the batteries together in South Africa. And then the fourth thing, the deployments team that I run is really about projects. So we're building a number of projects internally for our mines, and we're also working with a lot of project developers to help them understand VRFBs. But yeah, this is the Belco, which we're quite excited about. That's about halfway finished under construction in the East London IDZ. Some of the equipment arriving to be installed. Yeah, making 8 million litres a year initially, which is 200 megawatt hours, but that can easily be doubled or more depending on shifts or additional lines in the factory. The IDC, it's a JV between us and the IDC. With quite a big chunk of capex to build this project, and looking to make sort of 50 to 60 jobs initially, which would also go up as we scale. So here's just some nice photos of the building. Maybe looks like a plain building, but this is a custom built building for our process. And yeah, this is sort of a visualization of the project that we're building at one of our mines, which will be perhaps the largest commercially deployed battery when this project goes operational at the end of the year. So yeah, that's it from me. Very happy to take any questions, and yeah, I hope you guys and girls have all found that quite interesting.
Thank you very much, Frank, for the wonderful presentation. And the floor is open for Q&A. If you want, you can type your question. Otherwise, you can unmute and just speak. May I ask the Douglas or someone to enable?
I see some questions from Mondi. Hi, Mondi. Great that you're in the audience. I'll answer those from the chat. The electrolyte is toxic because it is basically a sulfuric acid or perhaps hydrogen chloride, but it's no more or worse than, say, lead acid, battery acid in terms of its toxicity. It does need to be managed properly. We have had the Department of Environmental Affairs review the electrolyte, and they've basically said that there's no special permitting or processes required around vanadium electrolyte. That the regulations that are in place around transporting and moving hazardous goods are quite sufficient. And the fact that this electrolyte is fully reusable at end of life, or actually that you can easily reprocess it, and that like I say, that's quite doable, also manages the end of life risk of that sort of hazardous material. And then I think you also asked, is it suitable for domestic? The technology is more suited for the grid scale, utility scale batteries. There are small units available, but the smallest unit I've seen has been a 10 kilowatt, 60 kilowatt hour unit. They're quite pricey. The value really comes at the scale. I think for anything smaller than a 1 megawatt sort of 1 megawatt, 4 megawatt hour project, it's probably not ideal. But it certainly comes into its own, like it has on those Chinese projects, when you start talking about, 50 megawatt, 200 megawatt hours, or 100 megawatt, 400 megawatt hours. That the technology can be, incredibly competitive, and the O&M cost per unit can come down quite significantly. And then I think you were asking about the job creation per megawatt hour. You would have seen that at our factory, this is just the electrolyte factory, that to make 200 megawatt hours would be about 50 employees. But there's obviously lots of other components that have to come into the battery. I think I missed mentioning it, but the tanks can be made locally, the pipes, the pumps, all of that infrastructure can be manufactured locally and brought to the battery. And there's obviously employees sitting in those factories as well. And of course, on the installation and the O&M side, there are also jobs to be created there. I don't see any other typed questions. I'm not sure if there's anybody else wants to either type a question or verbalize a question.
Chair, it's Monday here. Hi, Frank. Hi, Prof. Chandini.
Hi, Monday. Hope you're well.
So there are a few questions on the questions chat box there. I don't know, Prof, if you have seen them. There is one from Tristan, who is part of the Load Research chapter, and he's asking about the mines, the vanadium mines in South Africa. Are there many mines in the industry, or relatively few mines? Who own the resources? That is one of his questions. Thank you.
Sure, thanks. I see that I'm not able to see all the questions in the chat, so sorry if I only saw yours, Mondi. So please do read me the other questions. My understanding at the moment, and I'm not an expert on the mining side, is these are obviously the resources that we hold, and Glencore also is mining vanadium directly. But within the platinum belt, there are other vanadium resources that are available and that may not have been prospected. We certainly know that amongst the areas with platinum and similar resources, there is a lot of vanadium to be mined. But really, as primary production in South Africa, I think it's Glencore and ourselves. I'm sure there would be opportunity for other mining houses to participate if they had interest to do so.
Prof, I don't know if you've managed to get hold of the questions. And there is another question here from SAIEE Gura, our ex-president for SAIEE. Thanks, Sai, for attending. Sai wants to know, what is the largest BESS you can build? Is it a 1 megawatt BESS? Can you go bigger than that?
Sorry, is that asking that we can build in South Africa, or that's being built globally?
No, I think specifically locally, based on what Bushveld is working towards. Are you looking at a maximum of 1 megawatt in terms of your battery size that you can?
So the constraint is not really on the power side in terms of the megawatts. The constraint is more on the megawatt hour scale of the battery. In terms of, globally, you could basically get a battery of any size if you wanted to. But in terms of doing it locally, our initial production from the factory is going to be 200 megawatt hours, although that can be quite quickly scaled to 400 megawatt hours. So arguably, I guess if one battery wanted to get built in a year and wanted to offtake all of our production, conceptually that would be possible. But that would put the upper limit, for South Africa per year at this number. But like I say, if there was that demand locally where people were saying we need hundreds of megawatt hours of batteries in South Africa, by double shifting this plant, we can raise that to 400 megawatt hours, and then given another 6 months to install a second line, we could double it again. So the constraint actually then becomes the capacity of the mines. For that volume, the mines that exist can provide that volume. But if that were to scale, the mining activities would also need to scale quite quickly. So that becomes more an issue of time. If somebody came today and said, I need a 400 megawatt hour by the end of the year, we're not going to be able to do that locally. But if somebody came and said, we need you to deploy 400 megawatt hours of batteries over the next 3 to 4 years, and we're happy to have a deployment process like that, that would be completely doable.
Frank, I will request that you just keep your answers quite short and straight to the point. I see there is a number of questions that are coming in, which is great. There is another... I
will try to reduce my verbosity, sorry.
There's another very interesting question here from Eugene Kiston. Eugene wants to know mainly about the depth of discharge. So can you discharge at 100%, so meaning that you have got a 1 megawatt hour battery, can you discharge it all the way to 0? And what is the typical lead time? So I think he's referring to now you are building this plant. What is the typical lead time? Is it 12 months or 18 months or that sort of thing? Depth of discharge and...
Sure. So the depth of discharge, you can do 100% without negatively affecting the battery at all. So the battery can do fully 0 to 100% a rating without any issues to the battery to do that. And you can leave it also either at 0% or 100% without any issues to the battery. In terms of lead times, today the constraint is the supply of electrolyte in the global market. That to get any sort of volume in the megawatt hours, you're probably looking at a 9-month lead time. So I would say the earliest the fastest you could do a VRFB battery today would be 12 months, although that time frame is going to get shorter and shorter.
Yeah, I would expect it to improve as well. Then another question from Andre. Andre wants to know whether do you need a specific battery management system to monitor the battery facility?
Yes, so all of the VRFB manufacturers provide their batteries with a battery management system that looks after the battery and the DC side of the battery. A number of them also provide the PCS, the power converter system, the inverter side, and often they will also provide the energy management system that works with the inverter as well as the BMS for the battery to run the whole system. But yeah, absolutely, the DC block does require a battery management system to look after it. Yeah, and those are typically provided by the battery manufacturer.
Yeah, so Edgar and Ludwig, I think they have got very similar questions. So I'll take the one from Edgar. He wants to know the costs, and I think you mentioned your levelized cost. I don't know whether you had some figures at that point. So he wants to know the operational maintenance cost, refurbishment, and maybe you can just elaborate on your LCOE, whether you have some rough figures. Thank you.
Yeah, so LCOE, it obviously all depends on the application of the battery. So one calculates that value in a sense per project, and that's a lot of the work that we've done. I'm hesitant to give capex values without talking about a project, but what I can say is that for very big projects, we're seeing capex values on a sort of 4-hour battery being quoted under $300 a kilowatt hour from sort of 2024, 2025 onwards. So that's all in on the battery. And O&M, it's not significantly more than you would have on another battery. Yes, there are some moving parts in terms of the pumps, but the actual amount of time spent on O&M with the battery, as well as any, if components fail and need to be replaced, it's most likely to be the pumps, that's not a significant cost. So we don't expect O&M to be a significant cost issue relating to projects, typically under 1% of capex per year.
Another question from Ludwig. He wants to know whether you have any off-takers already for the electrolyte production that you are working towards. Have you already identified customers?
Yes, so globally we have significant interest from the battery manufacturers, and we are in the process of signing off-take agreements with the battery manufacturers for export. Locally, we haven't closed any projects other than our own project for the Vametco mine, where we will be building that 1 megawatt, 4 megawatt hour battery with the PV plant. That's the only, currently the only local project that is about to start construction. But we do have quite a lot of other projects under development. But what we've seen in like particularly in so certainly the public space, we'll be bidding. Well, we won't be bidding. We'll be working with IPPs to bid into the Eskom future procurement programs and the IPP office programs. But in the private sector, the main focus for us has been the mining space, and it's quite a familiar number that the mines already have something like 4 gigawatts of renewables projects that they want to build. Most of those projects don't need storage at this stage. Where we see like the private sector adopting batteries or large batteries is probably in about 2 years' time, when they want to build even more renewables, so that they can widen the percentage of renewables that they've got for their projects. And to do that, they'll need storage. So that use case, coupled with the tariff arbitrage use case, is what we think will drive the adoption of large batteries by the private sector in about 2 years' time.
I think I'll just pose the last question before I hand over to Prof to conclude the session. So one last question. You mentioned that, and this is from Karen Foslo. You mentioned that we can get as many, cycles out of the vanadium flow battery. And now she wants to know, what is the typical lifespan that you are looking at? And maybe just to add on that question, most of these energy storages, they come with life expectancy that is linked on depth of discharge, that if you discharge it at 80% and etc., then you can get so many. So what if you can just let us into that, and then Prof, you will take it from there. Thank you. So
typically, as I mentioned, the electrolyte basically has a very long life. So 40, 50 years. After every use in a battery, you would clean it, because it can pick up iron particles and other, just over time become slightly polluted. So you may clean the electrolyte, but the electrolyte, because it doesn't degrade, that's the great thing about the battery. There's also none of these requirements for you to run the battery a certain way to maintain the warranties. Typically, you can run the battery, within its specifications, of course, but you can run it as hard as you like. You can do 0 to 100% twice a day if you wanted with the battery, and you wouldn't have any degradation on the electrolyte. Of course, the battery itself, you have got moving fluids. Those moving fluids do eventually create wear on the battery itself. So typically, the design life of batteries is 20 to 25 years for all the other components in the battery. And so that's sort of the expected life of the battery.
Thank you very much, Monday, for conducting the Q&A session. And Frank, before wrapping up, I have one burning question. So hope that you can give a short answer to that. In the eyes of an investor into this business, what do you think the most significant competitor? Competitor in terms of the other product.
Yeah, so obviously lithium ion remains, by far the widest deployed storage technology. And it, you know, obviously, even though it has its weaknesses, if it were to get, you know, ridiculously cheap, like even significantly more cheap than it is today, then obviously it's going to dominate. But you know, what we're seeing is major supply constraints on the lithium side, and in fact, prices are likely to continue to go up because of the demand constraints around lithium. You know, apart from lead acid, the battery tech that is most commercialized thereafter is vanadium redox flow batteries. So we really do think that VRFBs can, in their long duration stationary storage space, give lithium a good run for its money. And there are lots of other emerging technologies where it's really hard. You know, there's ion flow, there's gravity storage. The issue with those technologies is they're not yet commercial. They're not yet scaled or being deployed commercially. I mean, we've seen like the gravity storage guys have had to radically redesign their tech because their crane version didn't work. You know, the ion flow stuff isn't built at scale or deployed, and maybe it will come and maybe it will be super cheap, but it's not there yet. So we certainly see that there is a window of opportunity in the next couple of years for VRFBs really to position themselves and be super successful within the stationary long duration storage space.
Okay, thank you very much. And why I asked that last question is we are planning to organize a panel discussion between the manufacturers and potential investors. We are planning to bring them to one podium and then see how we can exchange their views with the view of having a better South Africa at the end of the day. So thank you very much, Frank, and you will definitely be there in this event as well. So we are looking forward to seeing you again and again in the near future. So thank you very much,
and thank you for everyone who attended.
So thank you very much for your time and sharing of knowledge. And thank you very much, all of you, the attendees, for your time and your interest. And I would like to invite you all to be a part of SAIEE chapters, especially the load research chapter and the energy storage chapter. So you can contact either Monday or me to get any information, and you can also get information from SAIEE website. So with that, I would like to thank again to our resource person, Frank, and all of you. Have a wonderful evening. Enjoy the life. Take care. Stay safe. Bye.